Good day. So, in this lecture we will discuss about packet switches. That means, packet switches are switches which are specifically designed for handling packets. We have seen the telecom switches like space division, time division switches, etc. Okay, we have also discussed something about multi-stage switches which are used quite often in packet switches also, but in this lecture we will specifically discuss about packet switches, which is at the heart of almost all your computer networks. Okay. So, first just to give you some motivation that why do we require switches? The performance of a LAN can be considerably enhanced by moving over to switch LANs. Moving over from what? If you remember that some of the earliest kinds of LANs that we have just seen a brief glance of, some of them use shared memory like a hub or a bus, etc. Now, if you are using a shared medium, what is going to happen is that only two nodes connected to this LAN can communicate with each other at a particular point of time. Whereas, if you have a switch, multiple pairs of users or multiple pairs of nodes can communicate with each other at the same time. So, naturally you get a very good boost in performance of the overall LAN. So, that is one reason why we require switches. Of course, we require switches in other places also. Multiple distinct source destination pairs are able to communicate at the same time through a switch. So, that is why we require a switch in packet networks. A packet switch needs to look at the header of each packet to find the destination address of the packet. If you remember when we discussed about connection oriented and connection less systems, telephone networks are predominantly connection oriented, although connection less technology is also getting in there, but whereas data networks are predominantly connection less, although some connection oriented network technology is also there in some parts of the network. So, here today when we are talking about packet switches, we are specifically talking about connection less systems. So, in a connection less system, since there is no fixed connection between the source and destination which is held during a session, etc., such concepts are not there. So, each packet is on its own, and that packet presumably contains data from the source node which is meant for the destination node. It will contain a lots of other things like headers, etc., which we talked about when we talked about the ISI layers, etc. But we are specifically interested in the packets. That means, the data stream has been broken up into packets. So, each packet must contain the destination address of the where the packet will finally reach, because since there is no fixed connection, each packet must carry the destination address. And this destination address sometimes also called the MAC address. So, MAC is for medium access control. So, this MAC address of the packet, there are various types of MAC addresses, etc. So, we will come to that later on. Depending on the address, the packet is forwarded to another port. So, what happens in a packet switch is that through one port some data has come in. This data will contain a MAC address. Now, this MAC address is the address of the node, the address of the destination where it is supposed to reach, destination node. Now, this destination node, now the switch has to know that this destination is connected to this particular outgoing link, all right. So, there is a question of mapping from the MAC address to a particular output line, and if that output line has a tag, as we had seen in the earlier lecture on some of the switches that they use tags. So, if they have a tag, so depending on this MAC address, this tag would be sort of maybe looked up from some table or something and added to the packet, so that packet can make its way through the switch and reach the final output line, correct output line, and from then on to the destination station. So, depending on the address, the packet is forwarded to another port. Since more than one packet may arrive at different ports destined for the same output port, they may have to be internally queued. Okay. So, this was also discussed in the last lecture, that if we have more than one packet which is sort of destined for the same output port, obviously both of them, we cannot mix them together. So, one of them have to wait, and so one of them have to wait in some memory or in some buffer, or and maybe it will be queued, because there may be other packets coming up for the same port. So, they will all be queued, and this queue would be serviced by the output line one by one. That means, one by one it will be pumped out. The queue may be at the now the queue, you may queue it right at the input, seeing that the output port is busy, or you may queue it at the output port or somewhere in between. Not dropping packets and being fair to all input lines are desirable criteria for packet switch design. That means, we do not like to drop packets, we want to buffer them as far as possible. Of course, if a switch is of small capacity which is swamped by a huge number of incoming streams, etc., maybe for the same output port or something, the switch may be forced to drop some packets, but usually we would not like to do that. So, we would not like to drop any packet, and at the same time we do not want to starve any particular input line in general. In general, we like to serve all of them in a fair fashion. So, these are the criteria we use for evaluating a design for a particular packet switch. The first generation packet switch, it went through several generations, maybe now we are in the 4th generation or something. Anyway, the first generation packet switch, here it uses a CPU which stores packets received on line cards in its main memory. These packets are routed to output queues. The packets in the same queue are scheduled by software for access to the output line card. So, let us just have a look at this. So, it is a simple kind of situation. We have a CPU with some memory, there are particular input and output queues, these are the line cards. Now, what are line cards? Suppose this is a 6 port switch, as you see that there are 6 lines. So, there are maybe so many ports. Now, these ports are some of the functionality are sort of collected together, and they are implemented in a small daughter card kind of thing, which is called the line card. So, a line card will handle just a few of the lines, and there will be several line cards on the same switch. Okay. So, just if you go back, so these packets are routed. So, the CPU of course has some looking at the MAC address, looking up the particular, so what is the output port to which it must go. So, CPU has all that information, CPU does that lookup, and then it directs the packet to that particular output port where there may be a queue, and this queue is scheduled by software for access to the output line card. So, this was the first generation packet switch, which is fine, excepting that bringing in and that it is because of this CPU and memory storage, etc., looking up tables, etc., they take time. Okay. So, these switches were comparatively slow. Next, we came to the second generation switches. So, here some of the routing functions, you remember what is the routing function? In the routing function in general means that you look at the destination address and decide that which line, which output line this packet must go to. Okay. So, that is the routing function, and this routing function, if you are doing it centrally, naturally it will be slower. If you can distribute it somehow, so you distribute some of the routing functions to the line cards themselves. So, line cards which can switch locally if the destination is on the same line card. So, that is another point you can do, that if in a particular line card sees that the output destination will go through the same line card, then it through a particular line, then the line card need not send it to the CPU at all, this can switch it locally. So, that was one improvement over the first generation switch. Secondly, there is contention for the shared bus. So that is of course a problem. A contention for the shared bus is always a problem. and packets which cannot be routed is handed over to a central processor. So, the which cannot be, so the local line card does not have enough intelligence or knowledge to know how to route it. So, in that case it sends it to the central processor. In third generation switches, the shared bus is replaced by a switch fabric, which is an interconnection of buses and switching elements. So, the shared bus is replaced. If you remember that we can use a bus for broadcast etc., like we did in a knockout switch, but if I sort of and that may become a problem because of the contention for this shared bus. Now, we replace that by switch fabric, which is the interconnection of buses and switching elements. When a packet arrives in this third generation switch, which we will discuss in detail, when a packet arrives at an input port, it is tagged with the output port ID by a control processor. The switch elements automatically routes it to the correct output port, as we have seen as routing takes place in a min. The buffers in the switches can be associated with the input or the output or even with individual switching elements. The switch fabric may be crossbar, broadcast, Bayesian or other configurations. So, some of these configurations we have seen. You remember that crossbar switches, that means just a simple connection of switches. Then we have some broadcast like the knockout switch. It may be a Bayesian like a multi-stage switch or other kinds of configuration. So, there are three types of switching fabrics. One is that we switch it through the memory, other is you switch it through some shared bus, or you have a fabric of switching elements like I mean crossbar is the simplest kind of fabric. Of course, you can have more complex fabric over here, as we have seen, like multi-stage interconnect networks and so on. So, these are the three different types of switching fabrics that we have. Switching via memory, this was the first generation routers as we discussed. Packets copied by system single CPU. Now, speed limited by memory bandwidth, then 2 bus crossings per datagram. So, what is happening is that, so from the input port some packet is coming, then through the system bus it is sent to the memory where the CPU is looking into it and then decides that okay, this is the output port where it must go. Then it sends it back to the data bus destined for that output port catches it and throws it out. Okay. Now, this is the sort of part which gives a bottleneck to this entire scheme, because this part tends to be slow. Now, in modern routers, as I mentioned, input port processor performs lookup, copy into memory, etc. An example is that this is a sort of commercial system like Cisco Catalyst 8500 would take this kind of approach. Switching via bus, datagram from input port memory to output port memory via shared bus. Bus contention, so switching speed is limited by bus bandwidth. So, you have very fast buses like 1 Gbps bus for Cisco 1900, which is a low end Cisco switch. It has now been discontinued recently. Sufficient speed for access and enterprise routers, not regional or backbone. Okay. But this bus structure does not really work well for higher level switches. And one example of bus structure is a knockout switch, which we have already discussed. Just to recapitulate, we have n bus interface units, one for each outlet, and each takes input from all the broadcast buses. Each delivers output to its own outlet. Okay. So, this is, if you remember, that this is the diagram of a knockout switch. You have these buses on which the data is broadcast from the input side, and the output side, that particular bus interface unit for which it is destined, so that it catches that particular, others ignore that packet. So, it is queued up over here Q1, Q2, Q3, Q4 etc., and it is pumped out as per this queue on a first come first served basis maybe. Okay. This basis could be something else also, if you want to give some priority to some particular packets etc., is possible, but for in the simplest case this is a first come first served kind of queue. Switching via an interconnection network, just as in the other kinds of switches we have seen. So, it overcomes bus bandwidth limitation, that is the basic implication. As we want to go faster and faster, so we migrate from buses to an interconnection network. Bayesian networks, which we have already seen, or other interconnection nets, initially developed to connect processors in multiprocessor etc., they became useful in this class of switches, packet switches. Now, advanced design, this may involve fragmenting datagram into fixed length cells, switch cells through the fabric. Okay. This was an idea. For example, this is done in, let us say, ATM switches. So, in ATM switches what they do is that whatever be the packets, it may come in the form of packets or it may come in the form of streams on the originally, but it is finally broken down into fixed length cells. Now, the good thing about a fixed length cell is that you can I mean, if you know the length in advance, then you can handle, you can design hardware so that it can be handled in the fastest possible way. So, although the ATM cell is 53 bytes, so maybe inside the switch it is something like a 64 bytes. So, these 64 byte cells are fixed length cells and they are pumped as fast as possible. This is for designing very fast interconnection networks. So, we fragment them into fixed length cells. So, Cisco 12,000 switches GBPS through the interconnection network. So, when you go to this gigabit kind of switches, you require an interconnection network and maybe something more, as we will see. So, now as was discussed earlier, that we have three kinds of approaches to handling this contention and buffering etc. One is on the input side, one is on the output side, the other is somewhere in between. So, we will discuss these one by one. So, first let us come to the input side, but before we go forward, I just digress a little bit and just explain a little bit about what is involved in the input side, input part of the switch. If you remember our discussion about the 7 layer ISI models, so in the bottommost layer we had the physical layer, above that was the data link layer, above that we had the network layer, above that we have the transport and other layers which do not occupy us at the moment. So, we will look at these later, but we are having the physical layer, the data link layer and the network layer or the routing layer. So, these three are sort of very closely linked to a switch's operation. First, the physical layer, that means physically the link is coming in some fashion. Okay. So, that means, so there will be a certain kind of connector, certain number of lines are coming per input line. So, when we are saying one input line, but the one input line may consist of a number of wires when you are connecting. For example, if you are connecting through a Cat5 cable, there are a number of wires which go and connect to the that particular port. So, that is just a single port, all right. Similarly, in other cases, when if you have in the physical layer, if you have an optical connection coming in, so you must have an optical detector over there etc., etc. So, this also has, so this physical characteristics of the media has to be handled by the input port. Okay. So, we have, if you look at this picture again, so we have this just the input part shown over here. This side is the switch fabric, that means getting inside the switch. So, here we are sort of in the line card itself. So, first there is a line termination which takes its specification etc. from the particular physical layer that is being used. Okay. Then we have something like a data link layer functionality. Data link, one example of a data link layer kind of protocol is Ethernet. We will of course look at the details of Ethernet later on. But in the data link layer, what does the data link layer contain? The data link layer contains, I mean, we will not go into the details at this particular point of time. We will go into the details of Ethernet etc. later on, but in the minimum you should know that the data link layer contains the address the MAC address which we have talked about in the last lecture, the MAC address, the media access control address of the next machine to which it is destined. Now, please remember that these addresses are addresses of the machine, because the source node knows somehow, let us say it knows, it may not know that also directly, but anyway let us say that it somehow knows that let us forget about a large network. Let us now focus on a particular switch and some nodes connected to this switch. Now, this node A knows that I want to communicate with the node B. Of course, node A, B, etc., they do not have any meaning at this level. So, at this level some particular address is given called the hardware address, okay, which actually is the address of the networking card. If it is a computer that you have as a node, then the networking card of the computer, the network interface card, the NIC card, will have some address built into it in the hardware. So, this is the address. So, similarly its destination will also have another hardware address. So, this hardware address is put in the this data link layer part, and that means the data link layer puts this hardware destination hardware address into the packet. So, this address has to be read, and then somehow you have to make a mapping from this address, that okay, this particular address is connected to this particular line. So, you have to make that. So, for that you need some lookup, forwarding and queuing. If you are doing input queuing, you will do the input queuing also. What kind of lookup? So, this lookup will tell you that for this particular MAC address, that is the output line card. And usually nowadays what the switches do is that they keep on sort of getting this information in a dynamic fashion. When a switch is connected to a number of say computers is connected to a switch, the switch will listen to the network traffic and find out all the hardware addresses which are connected to these different lines. So, it will sort of slowly gather this information and store it inside. So, it will know that okay, this particular, so whenever some particular node is sending, it will give its source address also, source MAC address also. So, it will knows that gets the source MAC address. So, this particular MAC address must be connected to this line. So, this kind of information the switch keeps on gathering and storing it inside, and then so it may be some part of it may be stored locally in the line card, some part of it may be stored centrally, and there are thousands, and nowadays a switch can remember thousands of such MAC addresses which are directly connected to the switch. Okay. There is another problem, another level of problem, which is finding out about the addresses of remote machines, machines which are not connected to this switch at all, machines which are connected through other switches, routers, etc., in a different country maybe. Okay. So, that is a different problem, that is the routing problem, but in the data link problem we are concerned with all the MAC addresses of all the nodes which are connected to this particular network, which is local. Okay. So, that is stored in the switch. So, we look up that table and decide that okay, that is the final destination output line, which is the forwarding, and then you do the queuing, and then you send it to the switching fabric for its final destination. In decentralized switching, given datagram destination, look up output port using routing table in input port memory. Goal: complete input port processing at line speed. So, this is what I want to do. That means, at the speed, we do not want to hold up this particular packet to get the maximum throughput or the maximum speed. We do not want to hold up any packet in any buffer. Okay. Ideally, that is what we would like to do. So, we want to look it up in the locally at the input port itself, if that is possible. But please remember that even if you can do it at the line speed, the speed at which the packet comes, if you are doing it at the same speed, all this lookup business, even then you may be forced to store the packet for some time, because if you remember that either the output port where this particular packet is headed, that is already occupied because it is sending some other packet through it at the moment, or some intermediate switching element there may be a contention for an intermediate switching element, etc. For all these contention, etc., we may be forced to put this packet on hold even if we do the lookup at line speed. So, we have to queue this datagram. So, if datagrams arrive, and the other possibility is of course, if datagrams arrives faster than forwarding rate into switching fabric, and forwarding may be constrained by all these contention, etc., then you have to put it in a queue. So, what you can do is that you can put it in the input side, you can put it, you can buffer it at the input, called input buffering. Packets are buffered at the input, they are released when they gain access to both the fabric and the output trunk. That means, both the internal switching elements as well as the output port, both of these must be free, and then this packet may be released from the buffer which is held at the input. All elements except the arbiter, which is combinational, needs to run only as fast as the lines. So, this is an this is a good point about input buffering, that elements do not need to be faster than the rate at which the lines operate. Okay. In some other cases, we will see that we require faster speed anyway, but this has a big problem, this input buffering, which is known as the head of line blocking. Okay. So, let us look at head of line blocking. Just a minute. Okay. So, just let us look at the head of the line blocking. You see what is happening is here, you see there are 3 input ports, all right, and this is the switch fabric, there are 3 input ports, which is that this now the destination is shown by the color, that means red means it is destined for this particular port, blue one is destined for this particular port, green one is destined for this particular port. Now, see what is happening, the first packet red comes here and it goes to this output port. This one is also red, which means it is destined for the same output port. So, although there is no contention in the switching fabric, it has to wait. That is all right, that is accepted. The trouble is this green one, which was sort of destined for something in the middle and which could have gone through this fabric at the same time as this red packet is flowing at the top, this has to wait because the queue is blocked by this particular red packet. Okay. So, this is the called head of line blocking. At the head of the queue there is somebody who is blocked, and all the people who are behind or all the packets which are behind, they have to wait. This is called head of line. So, output port contention at time t, only one red packet can be transferred. So, green packet experiences head of line blocking. So, this is the head of line blocking, which is a problem with input buffering. Now, the other reason why you might require input port queuing is that fabric is slower than input ports combined. Input ports combined means it is the special case when all the lines are trying to pump data at the same time, all right. So, what you require is a sum total of all the speed that you get over there, which is not always possible, which is I mean usually not possible, because then there will surely inside there will be contention for the switching elements. So, you may you will be forced to queue some of these at the input. Head of line blocking, of course, we have already discussed. Queued datagram at front of queue prevents others in queue from moving forward. So, queuing delay and loss due to input buffer overflow. Now, this is the other thing which might happen. What might happen is that remember that this queue is given for each input port. Now, at each input port, how much, since they are not shared, now this buffer is not shared, this is only for that particular input port. So, naturally the size of the queue is limited. If it so happens that data is coming in at a fast rate and the fabric is very congested, so it is not getting a chance to go through, then this queue at the input port may overflow. If they overflow, which means that some packets have been lost. Of course, I mean this is a very undesirable situation, but this may happen. So, this is the head of line blocking. So, the other option is to buffer them at the output. That means, you have a queue, queuing buffer management, this part and the output part. So, it is being fed from the switching fabric, the queuing buffer management, data link processing, that means protocol decapsulation for the next jump, etc., and finally, the line termination. Once again you have to go to the physical layer over here, alright. So, this is the output port queuing. Now, what are the implication of output port queuing? Buffering required when datagrams arrive from fabric faster than the transmission rate. So, fabric is pushing datagram into a particular output line at a faster rate than the output line can pump out. So, naturally packets are getting accumulated near the output port. So, packets are getting queued over there, alright. So, you develop a queue. Now, now there is a scheduling discipline which we might choose, which chooses among queued datagrams for transmission, that which is the one which will get the higher priority, if you are putting some higher priority, etc. And there are, even if you are trying to give the same priority to everybody, it might so have happened that we might have kept one particular packet quite long in other places, sort of we kept it, maybe we fed it back or did something with it. So, it was already late. So, we might like to give it a higher priority than other packets, etc. So, there may be a scheduling which is going on in this on this queue. Buffers are maintained for each output line. This has a great advantage that this does not suffer from head of line blocking naturally, because it is being pushed in as soon as possible, but there are problems. Later stages of switch fabric and buffers have to be n times faster in the worst case to avoid dropping of packets within the switch. This makes the switches more expensive. Now, think of it that what is happening. What we are saying is that, suppose in the worst case all the n input, say all the n minus 1 input, n minus 1 input lines is trying to feed data into the same output port, alright. So, what is going to happen is that these packets which are coming at the line speed through n minus 1 lines, they sort of start converging to the nth port, alright. So, what is happening now? How can they converge? Obviously, if everything is operating at the same speed, then there is going to be contention in these switching elements, or one way to avoid this contention is to make these switching elements faster. That means, they will process the suppose two of them want to go through the same switching element, but suppose the switching element operates at double the speed. I am just giving a simple example, at double the speed. So, at the same rate as it is coming, it can push it forward. So, as you go more and more towards the output port, the speed requirement becomes higher and higher, and finally near the output, at the very point of the output port, it has to be n times faster approximately, okay, which is of course, I mean it is not done as like that, like n times faster, that is not possible, but the point is that this is a difficulty which we have with output buffering. So, although we do not have head of line blocking, but they tend to be more expensive. Maybe even more expensive if we have a buffered fabric, but this I mean of course, there is always a sort of trade off between the how expensive a particular switch is and what is its performance. So, naturally if you want to go for higher and higher performance where it is very important, then you need to sort of and that switches tend to be more expensive. So, one is that one is said that we have the buffer at the input, buffer at the output. Now, the buffer may be distributed in between or all over the fabric. The buffer is associated with each switching element which is used when the next stage is not available. It needs a lot of memory, and quality of connection is difficult to control. The point is that if with each throughout the switching fabric, if you have distributed our buffer, it is very difficult to have any kind of policy about priorities etc. So, the switches will handle it any way they can. So, we cannot really have a switch I mean policy which holds over all the buffers, because it is we do not have any processing capability over there, it is just a buffer and a switch. So, this is an example a switching fabric element. So, you look at this, that this is the switch in the center we have the switch, and then with the two input lines coming in, sorry, two input lines coming in, and then you have a buffer over here. If the next switching element is busy, then that particular this thing can be put in the buffer. From the buffer it will come back to the switch and then get switched when the next element is available. So, buffers need to be only in a buffered fabric, buffers need to be only as fast as an element's fan in ratio, and during overload the resulting queue is distributed. That is one good thing about distributing the buffer, which is that instead of putting all the buffer either on the input side or on the output side, as the output side gets more and more congested one particular area, what will happen is that the previous switching elements will also tend to get congested. So, they will buffer something and then the buffer would be pushed back. So, what is happening is that there is a distribution of this buffer all over the fabric, and that is alright. So, that these later stages need not be all the way up to n times faster than the initial stages, which is not always possible. So, that is one good thing about buffered fabric. Now, we will look at some examples of packet switches. One is that we will talk about 3 switches, let us say Ethernet switches, ATM switches and IP routers. These are all packet switches, all right, and all of them hold very important position, that means in the world of networking. So, we will just look at this one by one. Let us take up an ATM switch first. Okay, just a minute. Okay. So, let us look at an ATM switch first. In ATM, if you remember that in the ATM system we have fixed size cells. In the ATM world they are called cells, whereas in the Ethernet world etc. they are called packets, datagrams etc. Anyway, they are called cells. So, these are fixed size like 53 bytes etc. Now, each cell will contain a so called the destination address, and the destination address is in 2 parts. One is called the virtual path identifier and the virtual connection identifier, the VCI and the VPI in the virtual connection table. So, what happens is that ATM is sort of sets up a virtual connection. What is a virtual connection? A virtual connection is somewhere in between a physical connection on one side and completely connectionless let us say Ethernet packets on the other side. In a completely connectionless Ethernet packet, the packet contains the full destination, and at each node in between this destination is interpreted, looked up into some table etc., some algorithms run etc., and then you decide that what is the next step to go to. In a connection oriented system, a physical connection through the switches is set up from the source to the destination. In a virtual connection is also set up. So, there is an initial setup time for just as there is for connection oriented purely physical connection oriented systems. Similarly, for virtual connections also we need a setup phase, and then you can start communicating. In the setup phase, all the nodes in between know that we are going to have a session where this is going to be the destination. So, what would be its next address? It is computed just as like in a like let us say we do in an Ethernet etc., it is computed, but once it is computed it is coded in a very small VCI VPI kind of a few bits, alright. So, it knows that as soon as for this particular session and this particular session is identified by that VCI and VPI, that is the port I have to go to. So, this computation, this is done pre-computed at each of the intermediate nodes, and then the virtual connection is set up, that is all. Okay. So, there is no physical connection. So, as soon as there is some cell which is for this virtual connection, an intermediate node would immediately know that okay, this is the next step, and that is where it will push it. So, you do not have to do a full scale sort of lookup of a very big table. So, you have you look up only a very small table of VCI VPI in the VC table, replace but of course, virtual connections just as they are set up, they may be taken down. So, replace old VCI VPI with new ones, forward cell to outgoing interface, transmit cell onto link. So, this is the this is how an ATM switch works. So, if you so you see that the basic concept of the cell remains the same. That means we have some we have to find out the output port from the address, and here the address, once it is set up, after that the output the address is simply a small table of VCI VPI, which makes this lookup process much faster. So, this together with the fact that the cells are of same size, so you can develop your hardware in such a way, so that these ATM switches will work very fast. Otherwise, the rest of the switch and the switching principle remains the same as we have discussed already. Next comes the Ethernet switch, which is perhaps the most common type of switch that you see almost everywhere. As a matter of fact, this number of Ethernet switches which are being used and which are being put to use almost regularly is so high that the cost of these switches have also come down, because if you produce something in very large number, you can amortize the cost of its development etc. over a large number of switches. So, this cost of the switch comes down. So, Ethernet switches have become very cheap these days. Okay. A switch which used to cost maybe a lakh or so, maybe 10-15 years back, costs only a few thousand rupees today. So, this is the most common type of switch which we see everywhere. Now, Ethernet has to handle an Ethernet packet, and if it is an Ethernet packet, then it has to handle the Ethernet address which would be there in the packet. That Ethernet address is actually a 6 byte address. So, it is a 48-bit address. Usually, we do not get to see it as users, because this is a 6 bytes. It is very difficult to remember such a long address, and these addresses are really come in a very random fashion. So, it is very difficult to remember Ethernet addresses, but human beings need not remember Ethernet addresses. Ethernet addresses are sort of learned by the system when a system is put in a network, where the system may be a computer or a node, or the system may be a switch or a router. They learn about the Ethernet addresses, local Ethernet addresses which are there, they learn themselves. So, we will get into the details of Ethernet etc. later on, but anyway this lookup is necessary. So, the first step in the Ethernet switch is lookup frame destination address in forwarding table. If known, forward to correct port. If unknown, broadcast to all ports. So, this is what an Ethernet switch does. Suppose a packet has come with a particular destination address, and the destination address, if it is known that this particular address, that means the node having this particular address is connected to this particular port, then that becomes the output port for this packet. So, this output port is forwarded to the correct port. If unknown, you broadcast it to all ports. Now, why is this? If you remember, as I just now mentioned, or I mentioned earlier also, that these switches sort of they automatically learn from whatever is going on, they automatically learn the MAC addresses of the local machines. But suppose a switch is just in the beginning it is put in a network. Okay. Now, in the beginning it does not know anything, alright. So, what does it do? So, what it does is that as soon as it comes from some port, it broadcasts it to all the other ports. Now, it will listen and find out that which is the one which really was successful, and there are various protocols for finding things out. So, it will slowly learn. So, it may so happen that a switch may get a packet for which the destination address is not known to the switch. So, it will in that case broadcast to all the ports. Learned source address of incoming frame. One thing of course it has learned from this frame, although maybe the destination address was unknown, but it knew the source address. That means the source address came through this particular incoming link. So, this particular address must be, that means the node having this particular address must be connected to this port. So, that later on if this particular node comes as a destination, it knows where to send it to. Forward frame to outgoing interface, that is the other thing, and the transmit frame onto link. So, these are the various these things functions of an Ethernet switch. Then we have something called an IP router. All right, router, as you know, is a works at the in the network layer. It is not in the data link layer. That means a router has to decide that given some address. Now, this has a different set of address called IP addresses, maybe well, we are talking about IP routers. So, they are IP addresses. So, IP addresses, which is a sort of global kind of addressing scheme. There is some scheme for these IP addresses, although not as good as the telephone numbering scheme, but anyway there is some control, some central control. So, the job of the IP router is to find out that this is the global address that I have got. So, okay, maybe this particular node is in some other country. Okay. So, it has to understand that for going to that for reaching that final destination, I have to take this link locally, alright. Then it will send it to the next level, that is the data link layer, for that hopping that particular local link. So, once again we have the same problem, that we have got an address, some kind of destination address. It so happens that it is an IP address. Now, we have to do a lookup, we have to decide that this is the port it must go to and then send it to the port. So, in the same switch with some added maybe processing capability for doing, I mean a router usually has all kinds of other functionalities also. So, it needs some processor of its own, it needs some memory naturally for running programs, etc. There is some kind of an operating system which is there in a router. So, router is more complex, but the hardware part, the major part of a hardware, good part of its hardware are or is still the switch, and of course, the input and the output line ports, and usually a router can handle different types of ports. For example, just usually an Ethernet switch will handle only Ethernet ports. So, the physical characteristics or the physical layer properties of the ports are constant for all the ports, but a router can card different types of cards which can handle different types of ports, okay, maybe serial port, maybe high speed serial port, and all kinds of things. But the basic thing remains the same. Look up the packet destination address in forwarding table. If known, forward to correct port. If unknown, well, the router cannot broadcast it, because if all routers start broadcasting, then there will be broadcast all over the world through all the routers, which is not really acceptable at all. So, you can broadcast something only locally by an Ethernet switch. So, if the destination is unknown, if it has no way of finding out where to send it, it simply drops the packet. If when it sends, it decrements the time to leave, update, header, checksum. So, these are some side effects which it has to go through. Let me not go into the details of this, and finally forward the packet to outgoing interface, transmit packet on the link as usual. So, this is a router. So, we once again we have a switching fabric, we have input port and we have output port, and we have a routing processor. Okay. Now, let me quickly look at some of the issues in developing fast packet switches. First thing you must know, understand that the demand for communication speed is growing much faster than that for computational speed. You know, in computers there is this Moore's law which tells that every 1.5 years maybe the speed doubles, or the memory capacity maybe doubles, etc., etc. But if you look at the way growth has taken place in the communication field, especially with the speed of communication which is required, this is much faster than than the similar development in the computational area. There are two reasons for this. One is, of course, people are trying to communicate more. Okay, previously people were just satisfied with voice. Now they also want to send data, they want to upload or download large files, they want to send movies, etc. So the individual demand for bandwidth is growing, that is one thing. And the other thing is that more and more people are getting connected to the network. As more and more people get connected to the network, the number of possible connections goes up as n square if there are n people. So as n goes up, it goes up in the square. So but all this is going through the maybe some central backbone, etc. So at the backbone level, the speed requirement is very high. So we require very fast packet switches, and we will look at the just some issues over here. The main bottleneck in an ultra fast switch is the speed of memory used in buffers, etc. Okay. So this is the main bottleneck. For example, if you have a 5 nanosecond SRAM, static RAM, which is the faster kind of RAM rather than DRAM, and you have 64 byte wide bus. So you have what? 5 nanosecond per memory operation, that is your memory speed. 2 memory operations per packet, you have to write it there, you have to read it. So that makes it 10 nanosecond. Okay, and you have 64 byte, which means 64 into 8, 512 bits. So 512 bits you are handling in 10 nanoseconds, which comes to 51.2 gigabit per second, okay, which looks like a very high figure, but nowadays of course we get switches which have speeds of maybe 100 or 200, even 200 gigabits per second. So they are very high speed. So the buffer memory, this is the maximum. Of course this is not as simple as that, ultimately it comes to about 40 gigabits per second or so. So you use the fastest possible RAM, but even that is not enough. So we can take some possibility. One is the ping-pong buffering, that means packet comes over here. One is that so there are two buffer memories. One is that either you send it or you put it in a buffer like this. For example, when it comes, so maybe one of them is being sent while the other is being buffered, then this one will be sent and the next one which comes will be buffered. So you are trying to sort of double the speed at which it is operating. Of course you require two buffer memories for that. Okay, that is one approach. Okay. The other approach is to use multiple parallel buffers. Just instead of two, you have many of them and you put them in buffer in parallel. So you can go about it in a maybe in a round robin fashion or something, put them in multiple buffers. Okay, that is one thing. And the other bottleneck is that, suppose especially in a router, is that your processor, etc., if that is centralized, then that becomes a bottleneck for speed. So we have the so-called fork join router, where maybe you put a number of routers in parallel. Now these lines are coming at a particular rate, they are distributed over all the routers. So the routers individually do the lookup, etc., at whatever speed they operate on, and then they keep on pumping. This side is as well as this side, these are combinational, so they can operate very fast. The lookup, etc., that is parallelized. Okay. So these do not have any buffer in them. So routers, this part has the buffer. So this way, by going in for parallel operation, we try to make as fast switches and routers as possible. Okay, and this speed is going on increasing as and they have to increase in order to cater to the growing demand of packet switches and speed of packet switches and the capacity of packet switches all over the world. Thank you. Good day. So in this lecture we will discuss about SONET. The word SONET stands for Synchronous Optical Network, SONET, in the USA, Canada and Japan, or Synchronous Digital Hierarchy elsewhere. For example, in India we usually call it SDH. So, this is a time division multiplexing system that transmits a constant stream of information. Please look at this figure. So, we have what we have is that maybe we have some multiplexers. So, as the figure shows, so we have a multiplexer on this side, another, so which is output feeds to another multiplexer. This multiplexer, so this is going in this direction, then after some time the signal becomes weak. So, we want a repeater. That means, what is a repeater? A repeater is something which boosts the signal strength. So, there is a repeater, then it travels some more distance, and then there is a repeater again, and then it travels some more distance, and then on the other side now we have the corresponding demultiplexer, and then it feeds into the other demultiplexer. Now, from repeater to repeater we call it a section. So, or from a repeater to a multiplexer, this is also a section. So, multiplexer to repeater, repeater to repeater, these are called sections, and then from multiplexer to multiplexer we call it a line. Now, at the repeater nothing happens excepting the signal is cleaned up, okay. Signal may be boosted, or there may be other cleaning operation, synchronizing operation, etc., that may be done at the repeater, but as such the signals which are travelling here, the same set of signals are travelling here, okay. At a multiplexer, of course, some of the signals may go off in another direction, some signals may go in some other direction, etc. So, at the multiplexer there may be convergence or divergence depending on which way the signal is flowing. So, that may happen at a multiplexer. So, from multiplexer to multiplexer we call it a line, and then from the end user point to the end user point we call it a path. So, now the SP does not necessarily start in column 4, okay, which means that the SP does not necessarily stay within one frame. These are two very important points in SONET. The point is that although you have these 87 columns, but actually the data may get may start getting transmitted at some arbitrary point inside that 87 columns, okay. Now, what is the idea? I mean, why do you want to leave something and then only start from the middle? The point is that if there are some kind of mismatches of because of mismatches of rate, etc., etc., if everything in the world were absolutely synchronous, all activities and all equipments, etc., then you could have started from the beginning, okay. But that is not the case, and this is where we absorb this kind of variation, and this gives a great flexibility to SONET which was not there earlier. And the other thing is that, other interesting thing is that SP does not necessarily stay within one frame, which means that the SP may start in one frame and then end in another. We will just look at a diagram of this, okay. Let us have a diagram of this. You see the SP, this light green color, that really starts from somewhere, I mean somewhere after leaving some of the rows, okay, it starts here, alright, and the path overhead is somewhere here, okay, and there are two frames here. So, SP is really spanning both the frames.